So we're keeping going with velocity, with position, velocity, and acceleration. So we're looking at when is the velocity of the object equal to 54 feet per second. So again, we just take our velocity function. I have it right here. So our velocity is 48 t squared minus 72t. And when is that equal to 54? Well, this one, if you really wanted to try to factor it, you could try, but it wouldn't work. So we're just going to use our calculator. Okay, so pull up our calculator here. You could do one of two things to do this. You could either put 48x squared minus 72x on one line and 54 on the other, and then see where they cross, because that was where they would be equal. But I don't really want to put my window out that far to 54, so I decided to just subtract 54 from both sides, and I'm going to just see where this equals 0. So I'm going to see what x values make this true. Ooh, and that's ugly, so I'm going to go zoom 6. Yep, it's a quadratic, so it should have 2, so I'm just going to calculate those 2. So I'm trying to figure out where this is equal to 2, or to 0, so I'm just going to look for my left bound, my right bound. Alright, so we always go to 3 decimal places, 0.0549. And 2.049. All right, so if we go back, we just need to make sure that we label those properly. So this is seconds, and this is seconds because we just found what t values make that true. So it's at those 2 different seconds. Our velocity is exactly 54 feet per second. All right, displacement. What is the displacement of the object? So when we're finding displacement, this is what you're going to do. You're going to take the initial or the final position, and you're going to subtract the initial position. Because what we're trying to do is we're trying to figure out if it started here and it ended here, we need to find the distance in between those 2 objects if this is initial and this is final. Well, how do we find the distance between any 2 objects on a number line? We subtract. We take this one minus this one. Okay, so displacement is just final position minus initial position. So let's figure out what those are, right? Okay, where is it when t equals 2 or 0 and when t equals 2? So this is going to be our final position is s of 2 minus s of 0, because remember the s function, our position function, tells us where it is in space. So this would be 16x cubed, so that's 8, minus 36x squared, so that's 4, plus 24. That is s of 2. And then I just subtract 24 from it because that's s of 0. And I end up with 128 minus 144, which equals negative 16 feet. So what that means is that the object is 16 feet left of where it originally started, okay? You can just write negative 16 feet, that's fine, but it's 16 feet left of the initial position. Okay. Now it asks for total distance traveled. Now remember, distance and displacement are different. So displacement is how far away are we from our initial position. So it doesn't matter how many times we go back and forth, it's just how far away I am at the end. So distance is different. It counts every single time. Like if I go from here to my house and then back and then to my house and then back, my displacement is 0 because I'm exactly where I started, right? But my distance, I count every single time I went home and came back and went home and came back. I add up all of those. So how do we do this? So it just is asking between 0 and 2. So we're going to start with a number line here. We're going to say this is time equals 0. And this is time equals 2. And we're going to figure out what we're doing here. Okay? So where were we in space when time equals 0? What was our position? Well, our position was S of 0, which we found was 24. Okay, and then at time equals 2, we were S of 2, which is 8. Okay, so we could find displacement, but that's not what we're looking for. We're looking for distance traveled. So the question we have is were we always going in the same direction this whole time? Because if we were, then that's it, right? We just always went to the right, or we always went to the left. But we look back and we notice that we were not always going to the left or to the right. In fact, we have right here on our number line, first at 0, from 0 to 3/2, we were going left. And then from 3/2 on, we were going to the right. So we were traveling left until 3/2. We were traveling left, and then we were traveling right. So we traveled left, and we went a ways, and then we turned around and we went back. So we have to add both of these distances together. So we find where we turned around. We figure out how far we traveled here and how far we traveled here, and we add them together, right? Okay, so this is me traveling back to my house, and then I turned around and came back to school. So I add those two together. So how far was I, let's see, S of 3/2. Where was I when I turned around? So I was at 24 when I started. Where was I when I turned around? Well, if I put 3/2 in here, I get out -3. So I started at 24, and then I went all the way to -3, and then I turned around. So how far did I go from 24 to -3? Well, I went 27 feet total. Then when I was at -3, I turned around, and I went back to 8. How far did I travel then? Well, then I traveled 11 feet, right? So how far did I travel total? I traveled 38 feet. Here we have a graph showing the position function of a radio-controlled model car, and we have to answer the question. Was the car going faster at A or B? So this is a position function, and it's asking about velocity, because that's how fast it's going, right? So velocity is the derivative of the position. Velocity is the slope of the tangent line of the position function. So we look, would the slope of the tangent line here be steeper, or would the slope of the tangent line here be steeper? Well, when we look at it, this is actually, if I draw a tangent line, I'm so bad at tangent lines. You'd think a calculus teacher could do tangent lines, right? But no. There's there. And there's that one. They're terrible. But pretend like they're amazing, and you can actually visualize and see that the tangent line B at B is actually steeper. So it's at B because the curve is steeper. Steeper. It is not writing for me today. Okay. When was the car stopped? So again, we're talking about velocity. We're talking, and this is the position function, and we're asking when was the velocity 0? So in other words, when was the slope of the tangent line 0? Because it means we're not changing at all. Well, do you see from C to D we don't change at all? We actually stay completely in the same spot. That means we were stopped, right? So from C to D. From C to D, because the velocity is 0, because the slope of the tangent line is 0. At which point is the car's velocity the greatest? All right, so we've got to look at the steepest tangent line, And what we have to remember is that velocity has direction, meaning it can be positive or negative. So the greatest number has to be a positive number, okay? So at what point is the slope of the tangent line the greatest? Well, these would all be negative slopes, all of these, so they obviously can't be the greatest. And since we already know B is steeper than A, then it's B, because the slope of the position graph is the greatest there. Okay, and then it asks, when is the speed the greatest? Now remember, the speed is the absolute value. So if this is like, say, +2, and this is -4, the absolute value of -4 is +4, so this would actually be going, you would be going faster, you would just be going in a different direction. Okay, remember, because positive means we're moving right, negative means we're moving left. So at what point was this car's speed the greatest? Well, E, do you see how it tapers off here at F? If I could draw tangent lines. You need to send me back to college just to learn to draw tangent lines. Okay, if I drew all these tangent lines, wow, that's not even a line. We're going to pretend. Okay, which one has the steepest line? Well, it's definitely E, and since speed is the absolute value, we can have a negative, so E has the steepest line. And we could say the absolute value. Man, it is just not wanting to write for me today. Okay, the absolute value of the slope is the greatest there. All right, another example about vertical motion. So we have this position function for a ball that's thrown into the air from a high cliff. Find the initial velocity. So velocity, we don't have the velocity function. We need to find it, so we need to differentiate. So v of t equals -32 t plus 48. And then initial velocity as at time equals 0. So initial velocity, v0 equals v of 0, which is 48. And we have to label this, so it's it says feet per second, because we have feet and seconds. Okay, at what time does the ball hit the ground? So what does that mean? If you think about this, looking at this as a graph, if the ball is dropped, what's going on in the position function when it hits the ground? The position function is equal to 0. So hitting the ground would mean that the position function equals 0. So we're going to have the position function equal to 0. And we're going to take -16 out of that. And we have t squared minus 3t minus 10. And then we can factor that. So this is t minus 5 and t plus 2. And this still equals 0. And then that means that when t equals 5 or when t equals -2, the position function is equal to 0. So that's when it would be equal to 0. But wait, can time equal -2 in this example? It can't. Time can sometimes be negative and it freaks people out, okay? But in this example, we talked about time starting when they dropped the ball. So does time -2 exist in this example? No. So that one doesn't exist, so it hits the ground at 5 seconds. At what time does the ball reach its maximum height? Okay, so maximum height would be when it stops going up and starts going down. And when it stops going up, the velocity has to be equal to 0, right? Because that's the reason it starts going down, is because the velocity stops going up. Okay, so this is where velocity has to equal 0. So we have 0 equals -32t plus 48. We get 48 equals -32t, and that gives us t equals, should be -1.5. So at 1.5 seconds, our velocity is 0, which means that's where it reaches its maximum height.